everyone, and welcome to this new webinar. We are Martin and Maria, and today we're going to talk to you in depth about the Rise RMS220, a printer that not only stands out for its power and precision, but also opens the door to new opportunities in various fields from engineering to education, as well as healthcare and the automotive industry. The goal of this webinar is that by the end, you will have a clear understanding of what the RMS220 can offer, how it can help solve problems in your daily work, and especially what value it can bring to your organization. We're sure you're going to love it. Go ahead, Martin, with the presentation.
Thank you very much, Martin. Before we start talking about the printer, let's introduce Raise3D, the manufacturer behind this new LS printing equipment. This is a well-known manufacturer with 10 years in the industry. It is a global company with offices in Asia, the United States, and Europe. And it is one of the leading manufacturers of professional-grade 3D printers worldwide. It is especially well known for its CDM printers, which it has been developing for many years. However, it has recently expanded into resin technology as well, specifically with DLP technology, and now it has launched its first SDS manufacturing machine, which is the one we will be presenting today in this webinar. As we mentioned, it is a global company, and as of today, it sells its products in 173 countries around the world. Furthermore, as I mentioned, it is a well-known company, a well-established business. And as you can see, their printers are currently present in more than 15,000 centers around the world. These include companies, educational institutions, research centers, universities, and so on. Here you can see a small sample of some of the companies or organizations that use data and Raise3D, and you can see that there are some very important companies on a global scale. Within the Rise SLS 3D printing solution, we are first going to talk about the printer, the RMS220, and its main features. Perhaps one of the key points or most important features of an SLS 3D printer is its laser system. In this case, we have a fiber laser operating in the near range with a wavelength of 1064 nanometers, which is usually similar to what we can find in any other printer in its segment. However, the similarities end there. There are features that make this printer stand out significantly from other desktop devices and bring it closer, perhaps, to printers in the industrial segment, such as its power, for example. In this case, we have a laser with 75 watts of power. It's common for printers in this segment to have lasers with power between 5 and 30 watts. In this case, as you can see, we're dealing with more than double the usual power for this type of equipment. Additionally, another important point is the spot diameter. The spot diameter is the diameter of the laser's projection onto the powder bed, and it's the factor that will determine the resolution this printer can provide. In this case, we have a spot size of just 200 microns, slightly smaller than what we find in other machines in this segment, which guarantees us higher resolution and a better finish on the parts we produce with the 3D RMS220 network. Finally, perhaps one of the most innovative features, and what makes this printer one of the most productive on the market, is its galvanometer system. The galvanometer is the component responsible for projecting the laser beam onto the surface of the mold. And its speed will also determine the printing speed of the printer. In this case, we have a high-speed galvanometer capable of scanning at up to 30,000 millimeters per second. Both the high-power laser and the speed of the galvanometer will allow us to achieve high-speed printing on virtually any material. The next point I wanted to show you is the print volume and capacity. Despite being a compact printer or belonging to what we might know as in the desktop printer segment, this is a printer with a large manufacturing volume, perhaps close to that of industrial grade equipment. In this case, we have a build volume of 17 liters in a format of 220 by 220 by 350 millimeters, which is sufficient for most applications you might consider for this type of technology. Additionally, as I mentioned, the combination of a high-power laser with a high-speed galvanometer will allow us to achieve print speeds of up to 2.2 liters per hour for average packing densities of 20%. If we translate these speed figures into a more understandable productivity value, we can talk about an approximate capacity to produce up to 5 kilograms of polyamide parts per liter. Another important point, perhaps just as important as the laser system for an SLS printer, is the heating systems. In the end, temperature control in SLS printing is minimal, and it is what will determine the quality of the parts and their mechanical properties. That's why, in a printer mainly intended for functional or technical parts, having a quality laser and precise temperature control is fundamental. In this case, we have an infrared heating system that is divided into 4 independent zones. And with real-time compensation control, this means that during printing, those 4 zones are thermostatically controlled to regulate the temperature of the fusing agent. On the other hand, we have a maximum bed temperature of 220 degrees, which is enough to work with practically any SLS material, especially any polyamide, both polyamide 12 and polyamide 1, and a maximum piston and cylinder temperature of up to at 180 degrees, an average that is sufficient for most materials. Regarding speed, we did mention that the printing speed is very high, thanks to the combination of high-speed charging and high power output. But the printing speed or productivity is not only defined by the printing time, but also by the heating and cooling cycles. In this case, the printer's heating system has, thank you, with an advanced system that allows for preheating before printing in just 20 minutes, which is a very short time compared to other similar printers, where it's difficult to get below an hour or even more than an hour of heating time in a compact format, and also with smaller manufacturing volumes. And it also features an active cooling system that will allow us to reduce cooling times, which is also a significant part of the manufacturing process. Later on, we will provide more details about this cooling workflow and really see what innovative solution the country offers. Another important feature for working with technical materials is the intelligent atmosphere control system, which will allow us to work both with an air atmosphere and a nitrogen atmosphere, enabling us to work in an inert atmosphere. Martin, when we talk about the materials a bit later, we'll see exactly what benefits working with an inert atmosphere brings us. So when we discuss the materials a bit further on, we'll see exactly what advantages working with an inert atmosphere provides. But broadly speaking, what we are basically going to avoid by replacing the oxygen or air in the chamber with an inert gas like nitrogen is the degradation of the material due to oxidation. And this degradation by oxidation gives us 2 main advantages. On one hand, we are going to optimize and improve the mechanical properties of the part, since in the end we are working with a material that is less degraded, less damaged. And on the other hand, when we talk about SDS technology, the powder that we recover and want to reuse, the leftover powder we want to use in future prints, undergoes thermal degradation throughout the process, both from thermal degradation and from oxidation. If we avoid that oxidation, we also reduce the degradation of the powder, and therefore the amount of powder we need to refresh will be less, and that will have an impact on us, in that the cost of manufacturing or recovering the powder will also be lower. Understood? Thank you. Well, in this case, the intelligent control system not only allows us to select which atmosphere we want, whether it's an inert gas or an annular pressure, but it also has a series of components that will allow us to work efficiently with both atmospheres. On one hand, there is an active purge system. When we work with an inert atmosphere, it is essential to be able to purge all the air from the chamber and replace it with our inert gas to minimize the amount of oxygen and prevent oxidation. And on the other hand, we also have a SEPA filter system and an active drying filter, a 2-stage filter system that will allow the air coming out of the printer, thank you, whether we are working in open air or with an inert atmosphere, to be free of particles and volatile organic compounds, thus improving both the health and hygiene of the work environment. And finally, another key point is the possibility of incorporating a nitrogen generator on hand. When we work with inert gas or nitrogen in SDS, we need to keep a flow of air or nitrogen passing through the chamber throughout the entire printing process. In this case, if we use a supply of bottles or a tank, the consumption is quite high. Therefore, the expenses or costs that we have to allocate to that print will also be high. The advantage of incorporating a nitrogen generator is that we reduce those costs to a minimum, and we can also work in a more comfortable and efficient way. Another point I want to highlight about the RMS220 regarding workflow is its powder feeding system. In this case, it features an adaptive feeding system. First of all, we can consistently feed all materials, regardless of their flow. This is something fundamental in a printer like this, which will allow us to work with nylons as well as flexible materials, TPU, etc. A second key point is the capacity of the hopper. In the end, one of the limiting factors when working with printers like a considerable volume, a larger print volume, the SLS technology, is that the amount of powder we need in the hopper to feed the printer varies greatly, not only depending on the printer's build volume, but also on the packing factor we are going to use. Having a large volume, as in this case with 30 liters, and even expandable to 38 liters with an included accessory, will allow us to have enough powder capacity to be able to carry out full builds even with fairly high packing percentages or compaction factors. As we mentioned, both the feed system and the hopper have been optimized to improve powder flow, achieving a more homogeneous flow, free from defects or clogs, and finally, the powder distribution system is carried out using a dog bone scraper. That is, the distribution is achieved both by a translational movement of the scraper and by a rotational movement of the integrated roller. This serves to ensure a more homogeneous distribution and to avoid defects that could later appear on the surface of our part. As we mentioned, this is a desktop or compact segment printer. This type of printer, unlike other industrial ones, is aimed at all kinds of products. An industrial printer generally requires facilities adapted for its use, so let's say the workspace where we are going to use an industrial printer is already conditioned by the requirements of that specific equipment. In the case of desktop printers, the idea is that they can be installed in any type of location, whether it's a workplace, an industrial warehouse, or a small office, and that they can be operated safely. And additionally, the user profile is also different because in this case, we have to ensure that the printer can be operated both by technical staff who are knowledgeable about the technology and by people or users who are using this type of technology for the first time. To achieve this, Rise has aimed to create an interface and workflow adapted to all types of users. With virtually no prior knowledge from the very first moment, you can use the machine quite efficiently. To achieve this, I have incorporated a touchscreen, which serves as the communication interface with a large format printer. In this case, it's 10.5 inches and also high resolution, 2.5K. Another key point is the interface. Ultimately, to be able to work efficiently and without extensive knowledge, it's very important that the interface is adapted to all types of users and is clear and intuitive. This is something that characterizes all Raise3D equipment, and those of you who have previously worked with other printers from this manufacturer will know it well. You know that they are known for very organized, very clean interfaces where it's very easy to find functions and work with them. In this case, we'll find an interface very similar to what we can see in any other machine of this quality. It also features a system of notifications and maintenance assistance. This means that whenever necessary, when the user's attention is required, whether due to a detected problem or a maintenance routine that needs to be performed, the printer will send a notification to let you know that action is needed. And furthermore, in the case of maintenance routines, it will guide you on how to carry out the task completely. In addition to that, something very important when interacting with a printer is the safety measures. In this case, the typical safety features found in any professional grade printer have been included, as well as some from industrial grade equipment. For example, we find several emergency stop buttons. We also find something that is essential in any equipment that works with a laser system, which are the emergency or safety interlocks. These interlocks are a mechanical system that cuts the laser's power the moment we open any compartment or cover that would allow us access to the laser. And finally, we find a tower with a light and alarm that will allow us to detect any problem with the printer, not only if we are right next to the equipment, but also if we are farther away, drawing our attention to whatever the interlocks require. When we talk about SLS 3D printing, we can't just limit ourselves to talking about printers. That is, SLS technology requires a very specific workflow and a series of auxiliary devices. That's why in the case of Raise3D, we don't talk about a printer, but rather a solution. We have already presented part of the solution, perhaps the most fundamental part, which is the 3D printer with SLS technology. But now let's talk about the rest of the elements of the solution. The complete Raise solution is designed for a workflow that is covered from start to finish. That is, from the moment we have our design until we take out our fully post-processed part. And this includes several stages, both the slicing and manufacturing organization stage, as well as the actual printing process, unpacking, cleaning and post-processing, powder recovery, and also, let's say, something fundamental to the technology, which is the materials we will need to carry out the application. Now let's talk a bit about each of these elements. First of all, the manufacturing unit. The manufacturing unit is an element that forms an integral part, let's say, of the printer itself. That is, it is a modular component that will contain the piston and the printing cylinder. In other words, it's the volume where we are going to manufacture our parts. The fact that it is a modular component that can be removed is basically to facilitate the workflow and make it more convenient and faster. Why? Well, because as I mentioned at the beginning, the printing times or productivity when it comes to 3D SLS printing are not limited solely to the actual printing time, but a very important part of that total time is taken up by the machine's preheating and the cooling time of the powder block. Generally, or rather mainly, it's the cooling stage. If we integrate the build chamber and the cylinder into the machine itself, and there is no way to remove or take them out, once the print is finished, the machine is immobilized or rendered unusable until the entire cooling cycle is complete, which generally takes several hours. When we are able to carefully remove that particular cylinder, and those cylinders, as is indeed the case with the Raise, are thoroughly insulated, it genuinely allows us to perform a brief yet highly effective active pre-cooling process inside the machine, in this specific instance, lasting about 20 to 30 minutes. Once that initial cooling stage is finished, we can remove the build unit and let it cool externally, and load an empty build unit so that we can start a new print during that time. This will allow us to save around 15 to 20 hours, which is how long it would take for the powder block to cool down inside the machine.
A question that might be important: is it necessary to have more than one production unit, or is it not essential?
Well, it's not necessary, but it is recommended. In the end, if what we're looking for is productivity, it's basically what Krishna was explaining. If we have only one manufacturing unit, once the printing process and the first cooling stage are finished, we won't be able to use that manufacturing unit again until it has completely cooled down and we've removed the powder block. It would be the same as if the cooling happened inside the machine. In other words, the machine won't be operational. If we have an extra manufacturing unit, then while that unit is undergoing the final cooling, we can already start new production with the extra unit we have. This way, we significantly increase productivity and reduce working times by about 15 to 20 hours, as Antonio mentioned. And well, so basically, what we're saying is that this manufacturing unit will allow us to switch production quickly and carry out most of the cooling process outside the machine. Another key element of the workflow when working with SLS technology is the unpacking or post-processing units and equipment. In the end, when we print with SLS, it's not as immediate a technology as, for example, cooling technology, where once the print is finished, we have the application ready. When we finish a print using SDS technology, what we have is a block of powder, and inside that block of powder, our parts are buried. This means that we always require some additional steps, which involve breaking up that block of powder, what's known as unpacking, and retrieving our parts. The powder we recover needs to be refreshed in order to be used in future prints. Refreshing basically consists of mixing, in proportions specified by the manufacturer, used powder with new powder. And on the other hand, the parts we recover need to be cleaned, because there is always a fine layer of powder stuck to the surface of the part. For this, we have an all-in-one device, which is the C220P cleaning station. This cleaning station has the advantage that it allows us, on the one hand, to unpack and clean the parts, But also, and this is very important, it lets us recover and refresh the powder automatically. This unit is also designed to work in any type of facility. In other words, it doesn't require any special installations. In fact, it can even be installed in an office since it operates in a closed system with negative pressure, keeping the user isolated from the powder at all times. Furthermore, as we mentioned, the transfer from the printer to the unpacking station is done directly with the manufacturing unit, which is inserted and is compatible with both elements. And therefore, at no point are we directly exposed to handling the powder. Once we have the manufacturing unit in the cleaning station, this cleaning station has a series of features that also make it similar to the RMS220 printer. It is accessible to all types of users and also safe in any work environment. As we can see, there is a two-stage air purification system, in this case EPK activated just like the printer. The two stages allow us not only to filter out dust particles, but also volatile organic compounds, which, although not often discussed, are compounds that can be harmful and are generated during the fusion process of the plastic, in this case nylon. Additionally, as I mentioned, we have a compact design that also allows for easy mobility thanks to the wheel system and an interface similar to other Razor products, using a screen, in this case a 7-inch display, which is also quite large. Since this is a machine that also allows for material refreshing, its capacity when working with powder is important. In this case, we have two containers, a 20-liter container for new powder and a 20-liter container for used powder. This will allow us to process a significant amount of recovered powder. And furthermore, it is a fully automated system, which includes the material work trays and will automate the refreshing process and disposal for us. Here we're going to see in a short video just that stage where we remove the manufacturing unit after the initial cooling, the first cooling stage, and we take it to the unpacking station to work on it. As you'll see, it's a very quick, very simple process, and it also prevents us from being exposed to the powder at any time. Once inside the unit, we then proceed to carefully unpack, meticulously recover all the individual parts, and all of this entire process is done completely automatically. Now that we've seen a bit of the set of equipment or services included in the RMS220 printing solution, let's take a brief look at what the workflow would be. The first step is to organize the manufacturing process. Something very important in SDS printing is that the manufacturing cost is often determined by the powder we recover. In other words, the main source of cost in 3DS printing is not the material we use for the part, but rather the material we recover, because that's the one we actually have to refresh and which represents a processing cost for us. This ultimately means that it is a technology that may indeed require more careful organization or meticulous planning than some other comparable technologies, such as resin or filament printing methods. That's why it's very important to have powerful software that allows us to nest and organize the manufacturing process as precisely, compactly, and efficiently as possible. In this case, Rise uses IrriMaker. Those of you who have used printers from this manufacturer, even if they're from other technologies, will be familiar with this software, because it's the same software used for both CDM printing and resin. It's one of the most comprehensive slicers with the most features currently available in the printer sector, whether it's for resin or filament. And we find very advanced features that we can't find in other software. Of those features, in the end, they will also be available for SDS technology. As we go along, we'll also find other types of features like mesh distribution analysis, automatic starching, texture functions that are incorporated for other technologies, as well as the generation of manufacturing reports. And an incredibly important point when it truly comes to optimizing your valuable time and achieving the most streamlined or fastest possible workflow, once we officially start the actual manufacturing or the crucial staging and organization phase, the significant amount of time we diligently spend preparing the necessary files means that the printer can automatically and efficiently begin the printing process by preheating itself. This way, those 20 minutes of preheating required before printing can already start counting from the moment we begin preparing the files. This means that by the time we start printing, the printer will already be ready, and the printing or laser scanning process will be almost immediate. Once we have the files and send them to the printer, the second step is directly the printing process. It is an autonomous process carried out by the printer, and in this case it is very fast, as we mentioned before, due to the application of high-power lasers with high-speed scanning mirrors. Additionally, both the printer and the Idea Maker software will allow us to monitor the entire printing process in real time and see if there are any issues or to observe the success or progress of a job well done. The third step, which is not the end of the printing process, is cooling. In this case, as we mentioned, there is a brief internal cooling period, and once that internal cooling is finished, which takes about 30 minutes, we remove the build unit so it can cool externally, and we can insert a new build unit to start the next print job automatically.
So, what is the purpose of having active internal cooling?
Active internal cooling, what it generally allows us, these types of machines usually have passive cooling, meaning the heating is active. We have a system of heaters that will raise or increase the temperature of the powder. We reach that working temperature, which could be around 180 or 190 degrees approximately. Once the printing is finished, the heating system or the heater shut off and the print gradually decreases in speed or temperature. This process is very slow because in the end we have equipment that is very well insulated from the outside to maintain the temperatures and have precise control. So this passive cooling is very, very slow and gentle. This means that in many cases, the cooling times actually exceed the printing time itself. Having active cooling will allow us to ensure that this first temperature range, that initial cooling from almost the melting temperature down to the material's critical transition temperature, which is the critical zone, will be cooled using a very fast refrigeration system within those 30 minutes. Once we reach that temperature, just above the glass transition temperature, what we'll do is remove the moisture and then cool much more slowly, in this case with passive cooling inside the insulated unit. So this cooling process is actually very slow, but it needs to be very slow to avoid deformations or defects in the part. So that's basically the cooling process. An initial very rapid cooling inside the machine, followed by a very slow and gentle cooling outside the machine, which allows us to have parts free of stresses and deformations.
Perfect, let's continue then.
Well, once the external cooling process is finished in this first manufacturing unit, what we need to do is take this manufacturing unit directly to unpacking and post-processing, and that's where we'll begin the process of powder recovery and post-processing of the parts. Basically, this process consists of breaking up that block of powder or disassembling it, recovering the parts we have inside. On one hand, the powder from the block that we break falls through some grates and is collected in a container, the container we mentioned earlier for used powder. Then, automatically, the printer using the profile for that material will add the necessary amount of new powder to make use of the recovered powder, and it will mix it in parallel with that refresh. What we will do is use tools and suction systems to remove all the excess powder that remains on the surface of those parts. Now let's talk about materials. In other words, an SLS manufacturing or printing solution is nothing if we don't have quality materials to produce our parts. In this case, at the time of the printer's launch, we have a fairly complete range of materials which will be expanded in the future with both materials from the manufacturer itself and materials from the open materials system, which we will discuss next. Among the initial materials available, we will have 5 fundamental materials. First, we have a polyamide 12, which is the most versatile and most widely used material. Let's say it's the basic material for SLS manufacturing. It's a material with very good overall properties. We also have a polyamide 12 reinforced with glass microspheres, which basically provides, compared to standard polyamide 12, greater rigidity and higher thermal resistance. Another material commonly used in SLS printing is polyamide 11. Polyamide 11, unlike polyamide 12, has greater toughness and also allows us to produce models with more intricate geometries and thinner walls. Another key difference between polyamide 11 and polyamide 12 is that polyamide 11 comes from renewable sources, while polyamide 12 is a polymer, a plastic derived from hydrocarbons. Polyamide 11 is generally extracted from plant sources, in many cases from castor oil. And then we have 2 flexible materials. In this case, they are two thermoplastic polyurethanes with a shore hardness of 90. The difference is that we have a variety with a gray finish, which is the standard variety, and another with a matte white finish that provides a more aesthetic appearance and also allows us to achieve different color stains using synthetic dyes. The printer also features an optimized material cartridge, which means that the critical contact points with the powder are the material loading, the extraction of the powder block, and the post-processing of the part. As we saw, the transfer of the powder block is solved by using modular and removable manufacturing units, and contact during unpacking is also addressed through the use of the unpacking and post-processing station.
Martin, what does it mean that direct loading is done without contact with the powder?
Well, it truly means that being able to work without any direct contact with the powder during the loading process will absolutely guarantee us significantly greater safety and improved workplace hygiene for everyone involved. On one hand, the powder we're talking about has a very small particle size. In other words, it's not like working with sand, it's a very volatile powder. And even though the powder itself isn't toxic, working with suspended particles does pose a health risk. Normally, if we work with direct contact, it's necessary for us to use a series of fairly strict protective systems, such as particle filtering masks, sealed goggles, gloves, and fully enclosed work clothing. Working without contact allows us to safely relax the use of personal protective equipment, which means we'll have a much more comfortable workflow for operation and also a cleaner one. As we mentioned, this type of equipment is designed not only for industrial facilities but also for small businesses or offices. So in the end, having equipment with which you handle very volatile powder means that powder ends up spreading throughout the room. If you have other equipment in the same facility, it can become a problem for those devices if the powder gets inside, so it's something very important to consider. We mentioned earlier that industrial equipment, which sometimes requires more direct contact with powder, needs special facilities adapted to that technology. In this case, since the entire workflow operates without contact with powder, it ensures that this printer can be used safely and cleanly in virtually any type of facility. Fantastic. Let's continue then with the optimized material cartridge system. The optimized material cartridge is the container where we keep the powder we are going to use. This cartridge allows us to load it directly without any contact. In other words, we attach the cartridge to the printer, remove a hatch, and the powder goes straight from the cartridge, from the container into the printer without us having any, let's say, close contact. This results in simple and safe handling, as we mentioned, due to the system that avoids direct contact with the powder. Additionally, these cartridges are equipped with an RFID system to communicate with the printer and the workstation, allowing them to precisely identify which material we are using. This is very important because it not only ensures a more convenient workflow by eliminating the need to manually enter the type of material and its properties, but it also minimizes the risk of human error, such as confusion when selecting the correct material profile or using incorrect post-processing or powder recovery parameters. Here we're going to explain a bit more about what we mentioned at the beginning regarding the advantages of working with an inert atmosphere mode or an oxygen atmosphere. So mainly the advantages of working with a nitrogen atmosphere are that we avoid the oxidation of the powder batch. On one hand, this increases the printing speed and it also reduces the amount of refresh powder needed. As we can see in this table, if we work with a material like PA-DOC, which is the most common material in an air atmosphere, we would need to refresh at a 70-30 ratio. That is, in the final mix, 70% would be used powder and 30% would be new powder. If we work with the nitrogen silo, we would reduce that refresh rate to 80-20, meaning we would reduce the amount of new powder needed by 10%. As we mentioned, this also results in cost savings. For other materials, as we can see with AP, we reduce the amount of new powder by 50%. That is, in an air atmosphere, we would need half new powder and half recycled powder, but with nitrogen, we could reduce that to a 70-30 ratio. And even with CPUs, we would go from needing to refresh the powder to being able to reuse the powder exactly as it comes out of the printer. Not only do we increase the speed and reduce the amount of refresh needed due to material degradation, but this oxidation or degradation of the material during the printing process also means that the physical properties of the part are improved because we have a higher quality material. Additionally, it also prevents variability between production runs, which is something typical. Since we can't control the degradation and oxidation of the powder when working in an air atmosphere, it can happen that between different production batches, the mechanical properties of the final part show considerable variability. If we always work with a controlled, oxygen-free atmosphere, we eliminate that oxidation factor that can cause some variability, and we will achieve greater reproducibility and homogeneity between production batches. This is fundamental for many applications, especially those of a technical nature. Regarding material management and printing profiles, here we find several options in compact systems. There are manufacturers who, depending on their strategy, offer either closed material or system options, the possibility to open them, or directly closed systems. A closed system is one that only allows you to use materials provided by the manufacturer itself. In this case, your configuration options are limited solely to material selection. It does not allow you to control the printer's internal parameters, so to speak. To work with materials from other manufacturers or even with experimental materials, as is the case in research centers, universities, educational institutions, etc. Raise3D offers both possibilities. On one hand, we have the closed system with Raise3D materials that we saw earlier. It's a widely used system, produces high-quality parts, the powder prices are very competitive, and we have packaging compatible with the system. As we mentioned, the cartridges are optimized with RFID codes and the material profiles are fully optimized and refined, already loaded into the printer. Alternatively, we have an open system, and this open system actually works in two ways. On one hand, we have the traditional open license system, meaning we pay a fee to unlock the software license, and then we can modify all the parameters and use any material we want as long as we set the parameters correctly. Or we have the hybrid system, which is something innovative in this type of technology, and that's the credit system and the open material system. In this case, the open material program is a collaboration between Raise and various material manufacturers, in which Raise is responsible for the entire process of optimization and validation of those materials. This means that materials from other manufacturers, which we do not purchase directly from Raise, can still have their profiles provided by Raise, and this is done through the credit system. The credit system consists of a series of RFID cards that allow us to access the profile of a specific material and print a certain amount of that material. In other words, in this case, each card would allow us to print or entitle us to print 10 kilograms of the selected material. The system would work something like this. On one hand, we would have to purchase the material from the manufacturer as long as it is listed within Raise's open material system. And on the other hand, we would acquire from Raise the credit card that gives us access to the profile and the right to use 10 kilograms of powder. That information would be loaded into the printer and we could automatically start working with that material and print that amount of powder. It's a simple method to use since everything is fully optimized, and as we mentioned, just like with cartridges where we have our RKID code, in this case we have our material cards. It's an efficient method because the powder or the credits we use in a production can be restored to the card and we can keep printing with that same material. It's also an economical method since it's not necessary to pay for the full software license to test a specific material. We can simply, let's say, purchase the right to open parameters for a particular material, whether it's for a specific amount, to run a test or validate a material we're interested in, or for a very specific job where we might not need to do anything further. Another key point to highlight is that when we have the ability to work with different materials, it's also very important how easy it is to switch between those materials. In the end, when we talk about investing in SLS, we're talking about closed systems where there's a high risk of powder contamination, and cleaning in some cases can be very complex or tedious. In fact, some manufacturers, even though they allow multiple materials in their printers, recommend purchasing a separate printer to work exclusively with each material instead of using several materials in the same printer due to the risk of cross-contamination of powders or because of the complexity or laboriousness that this task can entail.
Martin, why is it important for the machine to be designed and engineered for material changes?
Well, it's mainly important because contamination of material or of certain materials can be critical and could even cause a malfunction in the machine itself. When we switch from a high temperature material to a low temperature one, generally there's no problem. For example, if we have a nylon that melts at a high temperature and we want to print with a polyurethane that melts at a much lower temperature when we print with the polyurethane, even if there are nylon residues in the printer, in the chambers, or in the insulation, it won't be an issue because since we're working at lower temperatures, that powder won't melt. What might happen is that we get some contamination of that powder in our parts. However, when we do the reverse, when we've been working with a low temperature material like TPU and switch to a high temperature material, if we don't thoroughly clean out all the remaining low temperature powder, when we start working with the high temperature material, that powder will likely melt due to the chamber temperatures of the new material. The powder that remains in areas like the recoater or in the insulation will become consolidated, which can lead to a loss of performance, a loss of insulation, or even a malfunction or damage to the machine itself. That's why it's important that DSBS machines or printers designed to handle multiple materials are developed with this in mind, that they have a modular system that allows us to easily access all areas that come into contact with the powder, and that there are no places where powder can seep in or accumulate. Additionally, working with, let's say, independent manufacturing units will also help us avoid a lot of complexity because everything related to the cylinder and piston assembly can be handled separately. We can simply focus on cleaning it since we can use an independent unit for each material. In this case, the Raise3D printer has been designed from the ground up with material changes in mind, and a modular, easily accessible quick-release system for the components has been implemented so that a complete material change process under optimal conditions takes only 45 minutes. Now let's talk a bit about the prices of these machines, because here we're talking about a DSLS printer or solution with features or capabilities that are superior to what we currently find in its segment, and that might lead us to think that the price is closer to industrial systems than to desktop systems. However, in this case, we see that the prices are very competitive. We're talking about a printer price of just 26,999 euros, the workstation at 7,999, and in total 34,998 euros, with an extra manufacturing unit or each additional manufacturing unit costing around 4,000 euros. As for material prices, we also see that they are very competitive compared to the usual prices for desktop construction equipment. We're talking about a cost per kilo of around 60 euros, and in this case, as we mentioned, the open material card that allows us to work with 10 kilos of material ends up costing just 12 euros per kilo. So each card gives you a cost of 120 euros, which is practically insignificant compared to the usual costs of machines for using fully open parameters. And that's the end of the presentation. If you have any questions,
yes, before we move on to the closing, we'll also open the chat so you can send us your questions and we'll answer them live. We're being asked, compared to other similar printers like Fuso or Deforms, what advantages does the RMS220 have?
Let's see. The main advantages are the ones we've mentioned throughout the presentation. That is, we have a fairly powerful laser system in addition to what's standard. In fact, I don't know if my colleagues can show a comparison that we put together internally about different printers in this segment so we can see the differences a bit more clearly. But anyway, we mainly have a printer that on one hand offers higher laser power and a much faster scanning speed than other printers in this segment. So here they show us the comparison. As we were saying, for example, the RMS has a scanning speed of 30,000 millimeters per second, while the Fuse One operates at around 12,000 millimeters per second, and the XX model of the Cyrex 7000. In terms of power, we see that other similar models operate at 30 watts, while here, as I mentioned, it's 75 watts. Another important difference is the working volume. In the end, we're dealing with a volume much greater than what we find in other types of machines. In this case, it's more than double the volume we have in the fuse. Then there are also the powder bed temperatures we mentioned earlier. In this case, 220 degrees, whereas other machines operate at around 200-210 degrees, which will allow us greater compatibility with more technical nylons. And well, regarding comparisons, we also did some examples, some simulations. In this case, since these machines are being very well received in the podiatry sector, we did a comparison of printing a set of 2 insoles. In this case, in 4 labs, the simulation gave us a total quantity of 12 units, that is 6 pairs of insoles, and the unit cost came out to 13.73 euros. The same models on the Raise allowed us to pack up to 20 units, that is 10 pairs, and we managed to reduce the cost to 7 euros and 74 cents, which is practically half the price compared to what it was in 4 labs.
We're also being asked here about part quality, specifically whether with the RMS220 you can achieve a part quality equivalent to that of an industrial SLS printer.
Yes, so when it comes to part quality, in the end we're working with similar materials and using the same technology. We have a heating system, a laser, so the quality, the finish, and the properties of the part are very similar, if not identical, to what we can achieve with an industrial system. What is the main difference that we find? It's more of an aesthetic difference. And here, as we mentioned before, we work with a laser in the near infrared, so we need materials that absorb more light. That's why we generally use dark colored materials, gray or black, which is what you'll find in all these types of machines. Industrial machines, in the end, use solutions or infrared lasers with a much longer wavelength, which generally allow you to work with white materials. So the main difference we'll find with industrial systems is that industrial systems will generally allow us to obtain white-colored parts, whereas here the parts will always be in a dark color, except for rare cases like the white CPU we saw earlier. But basically, that's the difference in terms of finishes. As for mechanical properties, they're very similar. I'd even say equivalent.
Very well, another question. I also think it's interesting. Is it mandatory to hire an installation or maintenance service? It's not essential.
It's not essential, as we said. This is a printer aimed at the professional sector, both for business and personal use, but it's not an industrial machine. Just as it doesn't require any special facilities for installation, it also doesn't have a very complex operation or require complicated maintenance. In fact, it's designed to be plug and play, and as we mentioned, the printer itself notifies you of any maintenance tasks that need to be done or any corrective actions, and it guides the user on how to do them. So it's a printer that most users could install and maintain themselves without any major difficulties.
Very well, perfect.
However, for anyone who wants to hire an installation or maintenance service or training, there would be no problem.
Perfect. So to avoid making today's webinar too long, we'll leave it here. If you have any questions that remain unanswered, you can send them to us by email or write to info@filament so we can give you a more detailed answer. If, after what we've seen here today, you'd like to take the next step and have this team in your company or institution, don't hesitate to contact us and we'll be happy to give you more details.
Well, thank you very much, Maria.